Luke said, when I was a graduate student, which is, it seems only yesterday, but actually it was 50 years ago, I realized to my horror. You could have counted the total number of people in the UK doing PDE on one hand. And there was probably almost nobody doing, well, two or three people maybe, who were doing any kind of analysis applied to light analysis. And at that time, Robert will know this well, that the British applied maths was dominated by Cambridge. It had a very strong fluid dynamics school, which at best ignored and at worst belittled anything that was rigorous. I mean, they would not have known anything about Larrey's work on Navier-Stokes in 1934, even in 1964. So, but things have really changed actually, and now there's quite a large community. But of course, PDE is just I mean, what Luke was describing was mostly sort of problems intrinsic to PDE, and there's hardly anybody in the UK doing that actually. I think rather PDE is a sort of, it interacts with so many different other subjects. One which is very strong in the UK is geometric analysis. I guess Britain has had a long-standing reputation in geometry. Then there's mechanics and physics and biology. So they both intersect with PDE and with each other. And indeed, there's an intersection of all three in some sense. And then there are things which are sort of, you could view as being parts of PDE, like the calculus of variations, which has some strength in the UK, nothing like Italy, of course, but some kind of strength. And then there are topics like geometric measure theory, which intersect with a lot of these areas. Not all the intersections are represented here, and which intersect with PDE. There are parts of PDE, spectral theory, which is strong in the UK. And then there are topics like harmonic analysis, which also intersect with PDE and numerical analysis. So it's a kind of a meeting point for lots of different areas. And well, it was difficult to judge. I spent quite a long time searching for all the people in PDE, but I found about 100 faculty who you could argue were working in PDE. That's certainly an underestimate, because I didn't look at every university in the UK, and I only know people in several universities, of course, but not in every university. So there might be 200 faculty, who knows, but still less than there are in Paris. But the people in Paris are more sort of uniform in terms of their interests, whereas this community has a lot of varied interests, which I think blend together in quite an interesting way. So one strong area is geometric analysis and geometric flows. So I try and list some of the people involved here, but it won't be a consistent list. Oxford has quite a strong representation. I should say in PD in general, there were in recent years, two centres for doctoral training, one which was in Oxford and one which was here in Edinburgh. And these have had some kind of an effect, I think, on the subject. So popular topics, how does this work here? So popular topics in this area are various flows, the Ricci flow, harmonic map flows, mean curvature flows, strong group in Warwick on some of these things, metric measure spaces, minimal surfaces, isometric immersions. These are common and popular topics. At the same time, related to this, there's a quite strong school in relativity, general relativity. Of course, Roger Penrose was a great instigator of a lot of this, particularly in Cambridge, maybe surrounding Mihalis de Fermos, who has some very high impact recent work proving the stability of the Schwarzschild family of black holes, together with Holzagel, Taylor, and I guess Rodniansky in Princeton. There's Chang Wong. So I have to say, well, Chang Wong is an example of a woman in PDE, but I can't say that our gender balance is really any better than in Vietnam. So there's quite a strong group in this area. In fluids, again, there's lots of different people around the country, and there's work on Navier-Stokes connected with regularity and turbulence. There's shock waves. I guess the unique exponent is Gui Chang Chen, who's a great authority on this. I'm not sure whether in Vietnam there are other things on sort of nonlinear hyperbolic systems, or because you mentioned hyperbolic equations, but more equations than systems. There's expertise on waterways with like John Toland and Tom Bridges, vortex dynamics, Manuel Del Pino and Monica Musso in Bath, non-Newtonian flow a little bit on Andre Sully in Oxford, for example. Okay, now the calculus variations and applications. So this is sort of closer to my own areas. There's again quite a group of people. That's not a complete list, I'm sure. So some of this work relates to the sort of multi-dimensional calculus variations, where the aim is to minimize some integral that depends on a vector-valued function. So omega is in general in Rn, where n is bigger than 1, and u is a vector rather than a scalar. So when both dimensions in the domain and the range are bigger than 1, then the theory becomes very considerably more difficult than it does in the case of when one of the dimensions is 1, because when one of the dimensions is 1, either the dimension of omega or its range is 1, then the key sort of condition which you see in sort of all parts of the theory is convexity with respect to the gradient. Okay, that's in some sense necessary and sufficient for the existence of minimizers, lying just a little. Whereas in the multi-dimensional calculus variations, that's replaced by a condition called quasi-convexity, which I don't plan to define today, but is a kind of Jensen's inequality with respect to gradients, and it's very badly understood. And the fact that it's badly understood has a lot of effects on very practical things concerning, for example, material science. And I guess probably the world expert is Jan Christensen in Oxford, and he's had a number of very strong students in this area recently. So now, as one kind of example of which there's been quite a lot of activity in the UK is liquid crystals. Actually, it's a very strong group in Scotland, in Strathclyde and in Glasgow University. So here there are essentially two different models of the same thing. One which is the older one, which is the Ozane-Frank model, where there's this vector field n that's supposed to. So liquid crystals are composed of rod-like molecules, so they're sort of arranged like my fingers and so on, wobbling around. But n represents the mean direction of those long molecules at a certain point x in the region, and it's a unit vector. So the functional is defined on you integrate some function of n, this unit vector, and its gradient. Now, another sort of model, more popular with physicists of the same situation, loosely speaking, is based on an order parameter q, which is a symmetric trace-free tensor. And typically, the behavior on the gradient of q means that this problem has smooth solutions. That's what's usually assumed. And so now, on the other hand, this problem up here has solutions which correspond to things you observe. For example, point defects, where n is x over the norm of x, for example. So vectors pointing outwards radially from some point. And so there's a lot of interesting work which has been done both by the Strathclyde group and by Luke actually, as to how you relate the sort of singular description of defects in this and related theories in terms of this smooth matrix valued field Q. So that's right. That's what is the relation between how defects are defined in the two theories. Now, what about solid mechanics and material science? So again, there's a large group of people working on different aspects of this around the country. So I thought I'd mention just one sort of result. I think it's kind of interesting because this is not the kind of work which will be done in Vietnam, for example. It's due to Philip Rindler. So he's a strong younger researcher in Warwick, and it is in some sense the calculus of variations, in that you've got some energy function associated with the problem for some function of C. But the idea is to somehow develop a dynamic theory of elastoplasticity. So there's an elastic sort of behavior which is given by this, but there's also plastic flow which is described by discrete dislocations. And he has a model of this flow by dislocations and a corresponding kind of dynamics. And so this is really sort of involves a lot of deep mathematics actually, and it's very much motivated by real application. So he shows that there's a well-posed elastoplastic evolution in which the plastic flow is driven by the movement of discrete dislocation lines. I don't think there's any work elsewhere in the world which is in some sense of this type. Well, that's about it, except there's lots and lots of things that I've not talked about. So here's a kind of list of sort of other areas which have good activity in the UK. Now, spectral theory is kind of interesting because it's dominated by Russians actually. So at some point, Russians came to the UK and they brought with them spectral theory of mainly linear PDE, and they attracted more Russians and they converted other people. So that's a very strong area in the UK, but one which I know very little about, and I honestly couldn't describe. There's reaction diffusion occasions. I think a big figure is Carrillo in Oxford, who does many other things, of course. There's work on nonlinear waves, Pierre Raphael in Cambridge, Hero O here in Edinburgh, and Pocovichnio, and integrable systems here at Herod Watt. There's a group at Edinburgh University in harmonic analysis. Actually, I think that's probably more or less the only activity in the UK in harmonic analysis, which has some intersection with PDE. There's work on computer vision around Carola Schoenlieb in Cambridge, and then Zheng Wei and Elaine Crooks. So we have two women there at least. And in biology, well, Maria Tashnik, we'll talk about that, and there's other activity as well. And then there's a little bit sort of in geometric measure theory. So it's kind of a broad group of people, but I think there's very little work in actual pure PDE. I hardly know any actually when you think about it. Okay, that's all I have to.
What do you expect the collaboration between UK and Vietnam in PDE?
Well, yes, I mean, I think that's a very good thing to explore. But somehow, I think the thing that would be of value is, in some sense, injecting some more applied problems somehow into, because the talent is obviously there to work on. I mean, because we saw sort of things that Luke was talking about, but somehow it's a little bit how PDE was in the UK, actually, maybe, or in the world generally, maybe 15 or 20 years ago. It feels a little bit isolated from the rest of the activity. I mean, this is very important work, pure PDE. I don't want to belittle it at all, but still, I think now interaction with material science and biology and so on, that's really important for getting increased impact.
Where do you think the future developments will be globally?
PDE.
Oh, well, have a try.
Well, I mean, essentially, systems of where would we like to have progress, and that's in systems of PDE of all types, which is more or less virgin territory. I mean, so even the calculus variations, which is the sort of simplest kind of area, we don't understand the basic convexity condition, and if you think about nonlinear hyperbolic systems, there's almost nothing in multi-dimensions.
But do you think the development will be driven by its relevance to physics and practical things, or will it be quite pure?
I don't think, well, I think that's idea of PDE at some point there is some physics direction. But what do you think, Robin? You're more experienced than me.
Not from Cambridge either.
I have a question that's somewhat more general, because I'm sort of a student of PDE because I just find myself a lot of affinity for, because I study statistics and probability, and I see that is a way to model the world, the randomness, and this is so there's a lot of application areas that is very natural. But of course, before people use probability and statistics, people use PDE to model the mechanics and the evolution system, right? And so I see a lot of questions that that run in parallel in the kind of research. And now in my tools, I want to analyze the system, I also draw from that. So is that a probability? It's not easy to characterize what is the open question of your field. How about in PDE now? Do you have sort of that is not too far that people actually
you can it's not driven by major open questions, I think. I mean, you can name major open questions like how do you characterize quasi-convexity or something like that. I mean, you could say that's in some sense an open question which is holding us back, but on the other hand, it's not really, it's not driven by such things. I mean, there is a limited amount of work on stochastic PDE in the UK, but not very much, actually. And also, there was one thing that I picked up from Luke's talk, which was when you talked about interactions with Vietnam. So there is one person who I didn't mention, which is Nikos Katsarakis, who works on this infinity of the Laplacian. I guess he's one. Maybe in some first.
Thanks as speakers today.